Okay, so in today's class we'll discuss contents of the module number 4. So as you all know, the module 4 mainly deals with hydraulic turbines. When I say hydraulic turbines, it is of 3 turbines we should study, as you have studied 3 steam turbines like Level turbine, Curtis turbine, and Parsons turbine. In case of module number 3, you will be going to study 3 different hydraulic turbines in case of module number 4, which is Pelton wheel, Francis turbine, and Kaplan turbine. So we will see what are these turbines and how they function actually. So the main difference between steam turbines and hydraulic turbines is, in steam turbine you are going to use steam as the fluid which energizes the turbine. Here, the water, just the plain water, will be used to rotate the turbine wheel. Okay, so by the definition of hydraulic turbine, you can refer this particular aspect. So, a hydraulic turbine or a water turbine is a prime mover that converts energy of falling water into mechanical energy in the form of rotation arc. So it is very simple to remember. Water energy is converted in the form of the rotation shaft, and this particular thing will be coupled to a generator by which you extract the electrical energy. Okay, let's quickly move into the classification, because the same classification you have seen in case of steam turbines, or you have seen the same classification, same type of classification in case of turbo machines as well. So we will see the same classifications for the hydraulic turbine also. So in the examination also, please be very, very careful about which class of turbine classification he is asking, whether he is asking classifications of turbo machines, or whether he is asking classifications of steam turbines, or whether he is asking classifications of hydraulic turbines. Please be aware of whatever he is asking. Please look into all those and then answer them. Okay. Now, so hydraulic turbines, primarily based on energy consumption, I have told you can be. Why now are joining? Okay, nice. We can classify into impulse turbine and reaction turbine, but this time we're having an idea that what is impulse turbine and what is reaction turbine. Can anyone see what is impulse and what is reaction? Anyone? What is impulse and what is reaction? Okay, I'll not waste much of the time here. So impulse turbine is a turbine which uses the kinetic energy of the incoming water. It is known as impulse turbine. The best example is the Pelton wheel. We have done the experiment in the FM lab as well. Next, you have a reaction turbine which uses both pressure energy as well as the kinetic energy from the incoming water. So for that, the best example is the Kaplan turbine and the Francis turbine. Even the Thomson turbine is also there. Okay, so best remember Kaplan and Francis. Okay. Next, based on the head, there is 3 different classifications, like there's low head turbine, medium head turbine, and high head turbine. For a low head turbine, the head will be less than 50 meters. If the head is less than 50 meters, then it is a low head turbine. If the head is between 50 to 400 meters, then it is categorized as a medium head turbine. If it is more than 400 meters, then it is categorized as a high head turbine. The best example of low head turbine is Kaplan, medium is Francis, high head is Pelton. Now, based on the direction of water flow, if the water flows in a tangential direction, then it is a tangential flow turbine. The best example you can quote is the Pelton turbine. If the water flows axial to the axis of rotation, then axial flow turbine. Then the best example is the Kaplan turbine. If the flow is radial in the sense, if this is a turbine wheel, 2 types of radial movement is possible. One is radially inward. Okay, so this is called as radial inward. And second one is radial outward. So both are radial movements. One radial inward and the other one is radial outward. So both of the movements possible, which is clearly defined here. So the best example for this particular turbine is the Francis turbine. You have even the flow turbine, the modern Francis turbine, which is the latest form of a Francis turbine. You have the mixed flow of a water between this. That means the incoming to this particular thing is radial and it leaves axial. So incoming has a one type of flow and outgoing has a one type of flow. So such type of turbines are known as the mixed flow turbines. The best example is the modern Francis turbine. Okay. Based on the specific speed as well, you can uh, classify the hydraulic turbines between low, medium, and high. For low specific speed turbine, it should be less than 60. For the medium, it should be 60 to 200. And for the high, it is above 200. So you have to remember all these values for the classification based on head and classification based on specific speed to write your answer very precisely. Okay, less than 60 is low specific speed, 60 to 200 is medium, above 200 is maximum, that is high specific speed turbine. So example for low is Pelton turbine, medium is Francis, and high is Kaplan. So please do remember all the examples, whatever we have put it in case of classification, if you want to answer the classification of the turbine. Now let us jump into the next topic, which is known as efficiencies of hydraulic turbines. So you have seen multiple efficiencies of the steam turbines, around 4 to 5 efficiencies you have seen. Similarly, we have couple of efficiencies, not couple, 4 of efficiencies of hydraulic turbines. Let us see what it is. In case of hydraulic efficiency, how would you define? It is the ratio of power developed by the runner to the power delivered by the water at the turbine. Hydraulic efficiency is the ratio of power developed by the runner to the power delivered by the water at the turbine inlet. You will see what is power developed by the runner is nothing but the turbine P by 60. Power delivered by the water at the turbine inlet. You will see how to calculate this based on your velocity triangle after that. Okay, next is mechanical efficiency. It's output by input, power available at the output shaft to the power delivered by the water to the runner. So it does not consider the hydraulic part of hydraulic turbine. It just considers the turbine part. What is the power made available by the water at the turbine? What is the actual power you are getting at the turbine output? So this particular thing is known as a mechanical efficiency. Okay. Next is volumetric efficiency. Volumetric efficiency is very easy to be understood. Suppose if I supply I give a vague value like 100 liters of water. If I supply to a Pelton wheel, it is not necessary that all 100 liters of water will be striking the turbine wheel, isn't it? Some may go out as a spillage in between in order to analyze how much percentage of water you have sent is actually striking the turbine wheel. We'll go with volumetric efficiency. So volumetric efficiency is the ratio of actual volume of water striking the runner to the volume of water delivered to the turbine. That means volume of water which is supplied to a turbine and actual volume of water which is striking the turbine. So if you take a ratio between these two aspects, you'll get the volumetric efficiency. So what is overall efficiency? So overall efficiency LF, you can just find out by multiplying the hydraulic efficiency and mechanical efficiency and volumetric efficiency. So if you multiply all these three efficiencies, you will get overall efficiency. But rather, if you want to define it in a specific manner, you can define as such as ratio of power developed at the output shaft divided by power delivered by the water at the turbine inlet. That means it is cumulative of hydraulic efficiency, it is a cumulative of mechanical efficiency, and even it is a cumulative of volumetric efficiency. So all these efficiency put together is known as overall efficiency. Is that clear? Shall we move on?
Okay, sir.
Good.
Yes, sir.
See, someone are listening. Nice. So Pelton wheel. I told you many turbines are you are going to learn in this particular module? How many turbines?
Pelton wheel, Francis turbine,
Yes, so
Kaplan
one is
turbine.
Pelton wheel, Francis turbine, Kaplan turbine.
Three,
So
sir.
we will cover all the theoretical aspects of Pelton wheel, Francis turbine and Kaplan turbine today's class. From Monday, we are going to solve the problems on Pelton wheel, Francis and Kaplan. Is it clear? So now already this will become very, very interesting and very easy. Why? Because we have seen the Pelton wheel in your lab, I guess, right? You have solved even experimentation on that, right? Correct? So the visualizing of this particular aspect of Pelton wheel would be very, very easy. Okay. So you have the constructional features. Do I need to explain the constructional features for you?
Okay, sir. Yes, sir.
Okay, fine. So it is very, very simple. You'll be having a shaft. On the shaft, you'll be having a dual-shaped, hemispherical-shaped cups like this. The hemispherical-shaped buckets or cups would be something like this. Okay, and this sort of cups would be mounted all along the circumference of the shaft. Now, water from the head. So, while the Pelton wheel is used, while the head of the water is very much high, you will use the Pelton wheel. So, that much high head water is being fed into the penstock. So what is penstock? There are two different pipelines I can say. One pipeline is known as a penstock. Okay. Other one is known as a tail raise. What is this penstock and the tail raise? So the penstock is the water inlet pipe and tail raise is the water exit pipe. Okay, all these things you have to understand. The water from the penstock would enter here. Okay, you have a nozzle and a spearhead like this. The movement of the spearhead using the nozzle will control the pressure of water striking the buckets. Okay, so once the water is striking the buckets, so it will be deflected on both the sides of the spherical shaped bucket. So one side is like this and another side is like this. So you'll be getting two velocity triangles at two exits and one velocity triangle at the inlet because it is going two ways. Understand? Okay.
Yes, sir.
So that is how it is. Now, because of impulsive action of not steam, impulsive action of water on the buckets, the Pelton wheel starts to rotate, and that particular is connected to the generator where the power is generated. As simple as that. Okay. So when you observe the velocity triangles of a Pelton wheel, it is very, very simple here. So this is your, now you have to concentrate guys. This is very important. Okay, please do concentrate now. So this is the hemispherical shaped bucket, which is considered as a blades for a Pelton wheel, right? Correct? Okay. Now, water is striking like this. Correct? Now, when the water is striking like this, half of the water is made to move like this, and half of the water is made to deflect like this. This is what is happening. I think there is a lag, I guess, right? A little bit of lag.
Yes, sir. Yes, sir.
No problem. No problem. I'll try to cover that. Okay. So because of this deflection of water, how much it gets deflected? It gets deflected through an angle of beta dash. It gets deflected through an angle of beta dash, which is a supplementary angle of beta 2. Okay. So just remember all these concepts. Now, if you observe the outlet velocity triangle, the outlet velocity triangle, whether there is any change in the outlet velocity triangle in the concepts whatever we have learned until now. whether there is any change. Concentrate on this one. The outlet velocity triangle. Is there any change?
Yes, sir. VU1, VU2 same direction.
VU1, VU2 in the same direction. Okay, that I'll come to that particular aspect. Now I am talking about only the outlet velocity triangle, not comparison between outlet and inlet, only the outlet velocity triangle. Is there any change in the outlet velocity triangle? I guess it is pretty much the same thing, isn't it? But can you observe any velocity triangle in inlet? Can you observe any velocity triangle in inlet? Can you? Is there any velocity triangle in inlet?
No, sir.
No. But if I say there is a velocity triangle at inlet, it is just one single line. Hope you are seeing it. A, B, C. So this particular single line is the velocity triangle for the inlet. Understood? We cannot see a complete velocity triangle. Just a single line will act as a velocity triangle in case of an inlet. Understood? So now A to B is U1, B to C is VR1, and U1 plus VR1 is nothing but VU1. So VU1 is also equal to V1. So only this constitutes the velocity triangle at the inlet. Understood? So where is the velocity triangle at the inlet? Only the line ABC will act as a velocity triangle at the inlet. Understood this point or not?
Yes.
Okay. So now, so two different aspects are there when it comes from an outlet. So you already know that when V2 comes in this particular direction, wait, I'll use another color. So V2, when V2 comes in this particular direction, the direction of VU2 would be in this particular direction. Correct? Now, when V2 changes its path like this, when V2 changes its path like this, then the direction of VU2 will change towards it like this. Correct? Yes, sir?
Yes, sir.
Okay, now, so in the first case, if you observe the direction of VU, the direction of VU at the inlet in this direction, and direction of VU in the outlet is in this direction. So observe the directions of inlet and outlet we use. In case of first, they are in opposite direction. If I go for second velocity triangle,
Sir, are these outlet
the
and inlet
direction of
triangles?
VU. Did not get you. The inlet velocity triangle is just a line like this. ABC is just a line. That itself is the inlet velocity triangle. Outlet velocity triangle would be of complete nature. Okay. So if you observe the second case, here the inlet VU is direction, and the outlet VU is also in the same direction. Some type of, in such cases, the VU, VU1 and VU2 will be in the same rectangle. Either the velocity triangle could be of this one, or velocity triangle could be of this one. It depends upon the problem statement. Okay. Next, coming to the, I told you there are a few of the formulas that have to be learned in case of design of tilt wheel, isn't it? So around 9 to 10 formulas have to be learned, I told you, correct? Yes, sir? In the class.
Yes, sir.
Same or the formulas are there here. I'll try to explain you one by one. Okay. First one is the coefficient of velocity of nozzle. See, coefficient of velocity of nozzle is what? It is the actual velocity which is striking the tilt wheel divided by theoretical velocity. Simple. What is coefficient of this velocity? It is an actual velocity which is striking the nozzle, striking the blade, divided by theoretical velocity. Actual velocity is nothing but V1, and theoretical velocity you can calculate by the formula root of 2gh. And this is how you calculate the value of CV. At the end, CV is given by what? CV is given by V1 divided by square root of 2gh. So this is the first formula you have to remember, where g is 9.81 and h is the total head which is available. Understood? So always CV ranges from 0.97 to 0.99. You just keep this particular thing in your mind. It says tangential or mean velocity. So tangential or mean velocity is given by the formula u is equals to pi into square root of 2gh. Okay? So tangential or mean velocity of the u is to calculate pi dn by 60. Here we'll be using the same thing with another form as phi into square root of 2gh, where phi is nothing but the speed ratio and it ranges from 0.43 to 0.46. Okay. Now, this is very important now. Jet deflection. So what is jet deflection? So the incoming jet is coming from this end. I'll just erase all this stuff. Okay. Now, incoming steam is coming, not incoming, water is coming from this end at this particular angle, and it is deflected all the way throughout like this. Correct? And it is deflected all the way throughout like this. Now, through how much angle it is being deflected? It is being deflected an angle of beta dash. And this particular beta dash is known as jet deflection angle. Understood? What is jet deflection angle? It is an angle through which the incoming jet of water is being deflected all the way throughout because of the blades. Okay. Now remember, always remember, your jet deflection angle would be equal to or will be supplementary angle of beta 2. What is beta 2? It is an outlet blade angle. Okay, it is a supplementary angle of beta 2, which is outlet blade angle. Suppose if in the problem the jet deflection angle is not specified, then you are supposed to take 165 as standard jet deflection angle if it is not specified in the problem, and this becomes an important point to be remembered. Understood? So if the jet deflection angle is not specified in the problem, then you are supposed to take 165 as the jet deflection angle, which is beta dash. Okay, that's great. Next, the mean diameter or the pitch diameter of the wheel can be found out using this particular expression. So you will be calculating by this one. Okay, you will be calculating by using this particular expression. U is equals to pi into square root of 2gh. You'll be getting u there. Now, in using pi dn by 60, since the speed would be known, you can calculate the diameter of the bent wheel, which is known as mean diameter or pitch diameter. Next one is jet ratio, another important parameter to be understood. It is defined as the ratio of diameter of the Pelton wheel to the diameter of the jet. Now, what is the diameter of the Pelton wheel? I'll go back to the Pelton wheel arrangement here. Now, you see here, I will explain the jet ratio. So, this is the diameter of the Pelton wheel. which is capital D, right? And what is the diameter of the jet? If you observe closely and zoom it out, this is a jet rocket is coming. If I mark a circle and calculate the diameter of that particular circle, this becomes the small d, the diameter of the. Understood?
Yes, sir.
So the ratio of diameter of the Pelton wheel, capital D, to the diameter of jet, small d, is known as jet ratio, small m. Understood? So what do you mean by jet ratio, small m? It is a ratio of diameter of the Pelton wheel to the diameter of the jet. Any doubts here? Any doubts?
No, sir. No, sir.
Okay. So that is the jet ratio. And why that jet ratio is so much important? Just because through that jet ratio, you can calculate what is the number of buckets required on a Pelton wheel. If you want to calculate the number of buckets required on a Pelton wheel, you can use this particular formula, which is Z is equal to 15 plus D by 2 into small d. Now you already know that capital D by small d is m. Before it changes to this particular 1 by 2 is 0.5. So 15 plus 0.5 m. Either of the expressions you can use to calculate what? To calculate the number of buckets. Next, number of jet required is obtained by, suppose if there is a Pelton wheel like this, okay, this is a Pelton wheel, and not necessarily that there has to be only one nozzle through which only one jet is striking the Pelton wheel. So it could be many of the nozzles like this, many of the nozzles all around the circumference of the Pelton wheel, striking the Pelton wheel. In this case, how many nozzles are there? 1 here, 2 here, 3 and 4. So totally there are 4 nozzles from which jet is creating on the Pelton wheel. So in this, the number of jets is 4. Now, how do you calculate the number of jets if it is asked in the problem? So you have to divide. That is, you have to divide the total rate of flow through the turbine by the rate of flow of water through a single jet. How you have to do it? You have to divide, you have to calculate the total rate of flow through the turbine divided by, we have to calculate the rate of flow through a single jet. If you divide these two parameters, you will get the number of jets. Suppose if the width of bucket is not specified, you can see the standard value of 5D. If the depth of the bucket is not specified, then we can take the standard value as 1.2D. So all these steps are to be taken when certain things are not given in the problem. If the certain things are not given in the problem, you are supposed to take all these values. If it is not given, width of the bucket is not given, you have to take it as 5D. If the depth of the bucket is not given, you have to take it as 1.2D. Clear? Any doubts about all these design parameters of Pelton wheel? Any doubts here? Are you able to hear me, guys?
Yes, sir. But
Okay. Connected to Wi-Fi as well. Okay, no problem. Okay. So expression for work done by the water and the pentan wheel is the first derivation. Second derivation is expression for the hydraulic efficiency. So these two derivations we'll just look at now. Okay. So consider the flow of water through a single bucket pentan wheel. The inlet and outlet velocity triangles are shown below. Remember, the inlet velocity triangle is just a line like this, A, B, C, where V1 or VU1 or V1 would be equal to U1 plus VR1. Okay.
Sir, your screen
Now,
is not visible.
screen is not visible. Is that the problem with everyone?
Visible.
No, sir, it's visible.
No, no.
No, sir.
Okay.
Sir, it's visible now.
Visible, huh? Fine. So the force exerted of water in the direction of motion is given by force is equals to mass into acceleration. You already know that. So when force is equals to mass into acceleration is nothing but the change of momentum, isn't it? So now mass, you can take it as rho A V1. I used another one. Rho A V1 is the mass of the water which is striking multiplied by change of momentum, which is VU1 plus VU2. So this is the Fx which is coming out, where rho is the density of the water, and A is the area of jet, which can be calculated by pi d square by 4. So where d is the diameter of the jet. Now continuing further, so you have calculated Fx, multiply it by U, so that you would get the value of W. So how will you do it? If you want to calculate W, it is same thing, rho A V1 into VU1 plus VU2 into U. So for the same thing, you are multiplying it by U. So the same units will come, Newton meters per second. So Newton is the units of Fx and meter per second is the unit of U. So it is Newton meters per second. Now, work done per second per unit weight of water striking per second. So weight divided work done divided by weight of unit water striking the second, that is given by. So this you have already calculated. So it is rho A V1 into VU1 plus VU2 into U divided. Now, weight of the water striking per second is given by rho AV into G. Weight is same, so I have to multiply it by G. So anything would get cancelled in this particular equation now? Anything would cancel? Rho A get cancelled and V would get cancelled, correct? So what is remaining? Remaining is U into VU1 plus VU2 divided by G. So this is the remaining factor, and this becomes the final expression for the work done per second by the water on the pentan wheel. So this is your final expression. Okay, is it clear? Okay. Next is expression for hydraulic efficiency. So you can have a question in an examination stating that derive an expression for hydraulic efficiency or show that the maximum utilization or for the maximum efficiency, the speed of the wheel should be equal to the half the speed of the jet. That means U must be equal to speed of wheel is nothing but U. Speed of jet is V1. So U must be equal to half of V1. So this if U is equal to V1 by 2, then there is a maximum efficiency or it is maximum utilization. Same conditions you have as derived for the Curtis, D-level and Parson. For every term there would be a condition where the maximum efficiency can be achieved. So for a Python wheel, you have to prove that the maximum condition in order to have the highest efficiency is U is equals to V1 by 2. Let us see how to derive this particular condition. Now, hydraulic efficiency of a Python wheel is given by work done per second divided by kinetic energy of jet per second. So, you know work done per second calculated in the previous one, it is rho A V1 into U into VU1 plus VU2. So, this is the work done per second. Now, what is kinetic energy of jet striking per second? It is simple half mv square. So, half m is nothing but rho A V1 into V1 square. Rho A V is volume, okay, not V1, it is volume into V1 square. So, now what happens? Okay, so all the things get cancelled here, correct? Whatever is remaining, would just write it here. Okay, square get cancels. Now, 2u, 2 I will take it to the top, 2u to VU1 plus VU2, VU1 plus VU2 whole divided by V1 square. So, this is what it is remaining. Okay. Now, again, the applications of velocity triangles would come now from inlet velocity triangle. You know that, you can see that VU1 equal to U1 plus VR1. So, I would take this particular thing as equation number 2 because we have taken this as 1 there. Okay. From the outlet, that is exit velocity triangle, apply cos beta 2. So, if you apply cos beta 2, where is cos beta 2? Beta 2 is here. Now, apply cos beta 2 here. It is U plus VU2 divided by VR2. So, from this, what happens? VU2 would be equal to VR2 cos beta 2 minus U. Okay. So, now I would take this as equation number 2. Sorry, equation number 3 now. So, I have the values of VU1 and VU2, which I am going to substitute in the equation number 1. So, I would just write what? I would just write substituting values of VU1 and VU2 in equation number 1. So, if you substitute the values of VU1 and VU2 in equation number 1, what will you get? So, you'll get this. So, I'll just write directly, it is efficiency, hydraulic efficiency is equal to 2U into, now substituting V1, it is VR1 plus U. Next, substituting VU2, it is VR2 cos beta 2 minus F. Okay, and divided by, you have V1 square. Now, I guess here plus U and minus U would get cancelled. So, if it gets cancelled, what is the remaining thing? Thing is 2U into VR1 VR2 cos beta 2 divided by E1 square. So, this is remaining now. Now, in the above expression, taking VR1 common in numerator, okay, common in the numerator. So what it happens if I take VR1 common? So efficiency hydraulic is equal to U is already there. You're taking VR1 now common, okay, into, so VR1 you have taken common, so it is 1 here, plus there is no 1, so have to multiply it by VR1 now into cos beta 2, close the bracket, whole divided by V1 square. So you all know that VR2 by VR1 is nothing but the value of K, which is friction coefficient. Which is friction coefficient. Okay. Next, also, this is the first point, you know. And second point, that the VR1 from inlet velocity triangle, it is equal to V1 minus of U, and hence what it becomes, efficiency hydraulic is equal to 2U into V1 minus U. You are substituting VR1 now into 1 plus VR2 VR1 K into cos beta 2 whole divided by V1 square. Next, the efficiency. The efficiency will be maximum for a given value of V1 when d by du of efficiency is equal to 0. So yeah, you differentiate the above thing with respect to u now. So d by du of same thing, right? 2u into v1 minus of f into 1 plus k cos beta 2 divided by v1 square. This should be equal to 0. So you want to differentiate with respect to u, take all the remaining terms outside. So 1 plus k cos beta 2 divided by 1 into d by du of 2u. I would just multiply, it would be easy for the differentiation. 2u v1 minus 2u square. So that is equal to 0. So now if I transfer this to either side, that would become 0. Now differentiating 2u v1 will leave to 2v1 minus 2 square differentiation. 2 into 2u, that is equal to 0. So from this 2v1 minus 4u is equal to 0. So from this, it is very much clear that u should be equal to v1 divided by 2. And this becomes the condition for the maximum efficiency, or to be more specific, maximum hydraulic efficiency. And if you want the formula for maximum hydraulic efficiency, what you are supposed to do is you have to substitute u is equals to v1 by 2 in the equation number 5. Have I written equation number 5? This is the equation number 5. Okay. So substitute to get the expression for the maximum hydraulic efficiency. Have to substitute U is equals to V1 by 2, then hydraulic efficiency should be maximum hydraulic efficiency. Any doubts here?
No, sir.
Okay. So continuing further. So only two derivations are there in case of your model number 4. There is no derivation asked in case of Francis turbine, nor in case of Kaplan turbine. Only you have two theoretical concepts of Francis turbine and Kaplan turbine, which we are going to deal now. Okay, we shall have to see just the constructional features of Francis and Kaplan turbine. So next, only that is enough for Francis and Kaplan. No derivations in case of Francis and Kaplan. So Francis turbine was the first hydraulic turbine with the radial flow design. Again ahead.
Send ಅದು derivation ಸ್ವಲ್ಪ send ಮಾಡ್ತೀರಾ ಸರ್ ವರ್ಧನ್ ಮತ್ತು ಎಫಿಷಿಯನ್ಸಿ
Work ಮತ್ತು efficiency
ಈಗ ಕ್ಲಾಸ್ ನೆಟ್ವರ್ಕ್ ಬರ್ಲಿಕ್ಕೆ ಆಗಲಿಲ್ಲ ಅದು
ಅರ್ಥ ಆಗ್ತಾ ಇಲ್ಲ, ಕೇಳಿಸ್ತಾ ಇಲ್ಲ.
ಸರ್ ಇದು ವರ್ಧನ್ ಮತ್ತು ಎಫಿಷಿಯನ್ಸಿ ಡೈರೆಕ್ಷನ್ ಈಗ ಹೇಳಿದ್ರಲ್ಲ ನೀವು.
ಹೌದು,
ಅದು ಸ್ವಲ್ಪ ಸೆಂಡ್ ಮಾಡಿ ಅಂತ.
whatever you are seeing content now, the same thing would be given you as a PDF in the form of notes. Okay? You can take a printout of it and attach to your notes. No need to write as well. Okay? Is it clear with everyone?
Yes, sir.
I guess my handwriting is legible, no? You can read with my handwriting. Any problem? No, it is bad, but it is manageable, I guess.
No, sir, no, sir.
Okay, fine. Okay. Okay. Sorry, I left the meeting. Okay. ತಾಳು ಇನ್ನು ಕ್ಲಾಸ್ ಮುಗ್ದಿಲ್ಲ, ಇನ್ನು ಫ್ರಾನ್ಸಿಸ್ ಕೆಪ್ಲಾನ್ ಟರ್ಬೈನ್ ಎಕ್ಸ್ಪ್ಲನೇಷನ್ ಬಾಕಿ ಉಂಟು. ಓಕೆ, ಇವರೆಲ್ಲ ಕ್ಲಾಸ್ ಕೇಳ್ತಿಲ್ಲ, ಸುಮ್ಮನೆ. Okay, now listen. So Francis turbine is a first hydraulic turbine with a radial flow design. So this was the first hydraulic. Okay, you cannot see the screen, no? Okay, share, start. Are you able to see the screen?
No, sir.
No, sir. No, sir.
Okay.
Sir, no, sir. Screen is not visible.
ಈಗ ಯಾರ್ಯಾರು ಹಾಕ್ತಾ ಇರಲ್ಲ ಅವ್ರೆಲ್ಲರಿಗೂ ಗೊತ್ತು, ಅವ್ರು ಯಾರು ಕ್ಲಾಸ್ ಕೇಳ್ತಾ ಇಲ್ಲ ಅಂತ ನೀಟಾಗಿ ಗೊತ್ತಾಗುತ್ತೆ. Okay, shall we start with Francis turbine and hardly take 5 minutes for Francis and 5 minutes for Kepler? Shall we start?
Okay, sir.
Yes, sir.
Yeah, yeah. So Francis turbine
Okay,
was the
sir.
first hydraulic turbine with the radial flow design, which was designed by scientist known as James Francis, and hence it is called as a Francis turbine. Okay, however, you know that the modern Francis turbine will be of a mixed flow type, mixed flow reaction turbine. Now, normal Francis turbine, which was invented earlier, it was a inward flow type, radial inward flow type Francis turbine. Okay, we'll be having 2 to 3 parts in this: runner, guide, spiral casing, and draft tube. Runner is a spherical circular wheel which is fixed. Blades are attached. Now count the blades number. How many you have? How many blades you have in case of Francis turbine is 16 to 24. So more number of blades will be there in Francis turbine. But when you go for a Kaplan turbine, you'll be finding only 4 to 6 of blades. Okay. So in cases of Francis turbine, you'll be having more runner blades. Okay. So guide wheel. So this guide wheel is a stationary wheel which is around the runner of the turbine. Okay, so number of blades are fixed around the circumference of the guide wheel so as to allow the water to a certain angle. So this guide wheel is there. No, this particular guide wheel, or it is also called as a stationary wheel, which is used as a nozzle. Okay, there is no nozzle in case of Francis turbine. No, so this is used as a nozzle to guide the water into the runner. Okay, spiral casing, or it is famously called as volute casing. So this guides the total water into the turbine. So what is the function of draft tube? I will just explain you while going into the turbine. So this is the cross section of the turbine, you can see. Okay, so the water comes and goes like this and comes like this. So this is the way through which the water gets in the turbine, rotates radially, comes to the center of that turbine, comes to the center of the runner, and then comes with the help function of a draft tube. Now, draft tube is necessary. This is very, very important question in case of your examination. Many times he has asked why draft tube is necessary in case of Francis or Kaplan. Without draft tube, can the Francis or Kaplan run? So if the answer for this is no, draft tube is 100% necessary.